log x over log 2. Now, you're going to learn, when we get to this unit in more detail, the change of base formula. But something that you just, basic stuff is this step here. Just remember that whenever you have two logs that are dividing, like this, you can rewrite that as log base b m. So your numerator is the value that goes here, and your base for the log is your value that was in the denominator. So in this case, it's going to be log base 2 x equals y. Now this is a little confusing, especially if you haven't really dealt with logs before. Remember, when we're dealing with exponents, they always have a base value. For example, 3 to the power of x, 10 to the power of 7. In this case, my base value is 3. In this case, my base value is 10. It's the number that's being multiplied, repeatedly multiplied. That's what exponents do, right? So this is the same thing as 10 times 10 times 10, 7 times. That's what exponents are. So the base value, and then the exponent. So just like that, logarithms also have a base value. So every single log has a base value, and depending on what you're dealing with, usually the log within your calculator is log base 10. That's like the generic rule. So log base 10, so anytime you plug in, let's say, log of 2 in your calculator, you're technically doing log base 10 of 2. So just be aware. There is another special case when it's log base e, that's called ln, and not entirely sure if we're going to cover this within this course, but that's something you should maybe know. But yeah, so special cases, definitely something you'll learn in university for sure. So that is log base 2x. This is the change of base formula for logarithms. And this is how you can kind of calculate using your calculator, because as it stands, you can't really do log base of 5, let's say 10 on your calculator. You wouldn't be able to do this in your calculator if this is all that was given. Like you can't just punch in log 10. That's not going to give you the right answer. You have to kind of do a change of base formula to figure out that this is equivalent to log of something divided by log of something. And remember, the denominator is the base value, so log of 5. And the numerator is this value here, so log of 10. So the way to solve this equation, log base 5 of 10, in your calculator is to punch in log 10 divided by log 5. And that will give you a number. And that's how you solve it. Just something, we'll probably get into a little bit more later on. Okay, now let's graph both of them. I am just going to take the table of values here. So exponential functions, remember your key points, -2, -1, 0, 1, 2. Your y values, just plug it in. So 2 to the power of -2, which is 1 over 4. 2 to the power of -1, which is 1 over 2. 2 to the power of 0 is 1. 2 to the power of 1 is 2. And 2 to the power of 2 is 4. So these are my points. And an exponential function is blue. It goes like this. It goes up, and it has that y-intercept of 1. Now, in our red, we have our inverse function, log base 2 of x. And if you're not sure how to get points for an inverse function, it's very simple. You first make the table of values for your original function, and then you just swap your x and y values. So the y value, that's 0.25, is now our x value for our inverse, and the x value, which was -2, is now our y value. So you just swap the values. You can see the pattern there, and just graph these values. And if you graph them, you kind of get a graph that looks like this in red. And this is the inverse function of f of x. And you can see that if I drew this diagonal at y equals x, and if this is a mirror, then these are reflections of one another. So graphically, this is what it looks like to draw a inverse of a function. And algebraically, we can solve it using the equation, and we can use the table of values to help us. And to complete the chart, this is pretty simple as well. Your x-intercepts for an exponential function, there are none. Doesn't intersect. There's an asymptote there, horizontal asymptote, so it doesn't intersect the x-axis. Y-intercept is 0, 1. Domain is x belongs to all the real numbers. Range for an exponential function, well, you can see clearly the blue function here only exists above the x-axis, so it has to be y greater than 0, and it's not equal to 0 at any point. And the asymptote, there's a horizontal asymptote at y equals 0. Now for our inverse function, the x-intercept is 1 and 0. So see how the y-intercept for the original function is now the x-intercept, and it's at 1, 0, because we swapped the values from 0, 1 to 1, 0. Y-intercept, there is none. See how there's no x-intercept initially. Now for the inverse, there is no y-intercept. Domain, see how the domain for the original function was xer, and now the range is yer. Kind of got swapped. And the range for the original function is yer, y greater than 0. Well, now it's xer, x greater than 0 for the domain for the inverse function. So you kind of just swap, you're just swapping a lot of x and y's when it comes to inverse functions. And then for the asymptote, there was a horizontal asymptote, so now there's a vertical asymptote at x equals 0. So pretty straightforward stuff when it comes to properties and inverse functions. Let's move on. What is a logarithmic function? The logarithmic function is the inverse of the exponential function with the same base. So the log function is defined as y equals log base b, x, or y equals the logarithm of x to the base b. The function is defined only for when b is greater than 0 and b cannot be 1. In this notation, y is the exponent to which the base b must be raised to give the value of x. I'm going to show you what that means in a bit. In other words, the solution to a logarithm is always an exponent. Yeah, that's important. The logarithm function is most useful for solving an exponent. Yep. Common logarithms are logarithms with a base of 10. It is not necessary to write the base for common logarithms. Log x means the same as log base 10x. So that's what I mean. When you're dealing with logs with base 10, that's like kind of the normal common base. So you don't really have to write the 10. You can just write log x. This is important. Changing between exponential form and logarithm. So here we have an exponential and log expression. So y equals b to the power of x. That's your exponential expression. Why? Because there's an exponent. See that? Very simple. And we're going to convert this into a log expression. I don't know. It's a log expression. Well, there's a log there. That's and the way to do this is, well, what's your base value? Remember, the base value is b. The base value is always the base value, whether it's in exponential form or logarithmic form. So that is always going to be the base value. So I know for a fact that my log is going to have a base value of b in this case. The other thing you need to know is when you're dealing with this, I guess I'll show you the steps. Essentially, to convert from exponential form to log forms, you're taking a log of both sides. Log y is equal to log b to the power of x. Now, remember when I said your base value for a log is always b? So this can be log base b. There's a few ways of doing this, but I'm just going to kind of teach you this way. So if I take log base b of both sides, what does that do? Well, first things first, this is log base b of y. Nothing really to simplify here. The x comes in front, so we have x log base b of b. And something you will learn when it comes to logarithms is that when you're taking the log of something that has the same base, like if I were to take the log base 10 of 10, that's equal to 1. If I were to take the log base 2 of 2, that's equal to 1. If I were to take the log of 100, but the base value for the log was also 100, well, that's just 1 as well. Kind of like anything to the power of 0 is 1. Kind of like that. So we know that if I were to take the log base b of both sides, and there's a reason why I chose base b, because This